So I think it's clear. For any system, the minimum number of phases is 1. Whether it's one component systems or two component systems or three component systems, for any type of systems, the minimum number of phases is 1. Suppose if I select a two component system, and if I take the number of phases as 1, then the degrees of freedom f is equal to c minus p plus 2. This is the phase order equation, and here I have selected two component system, and the minimum number of phases for any system is 1. So I have taken minimum number of phases here. So then this becomes 3. F is equal to 3. That means you require 3 variables to describe this phase for a two component system. Okay? Therefore, 3 variables are required to describe any phase for a two component system. Okay? And what are these 3 variables? The 3 variables required to describe the phase in a two component system is: number 1, temperature; number 2, pressure; number 3, composition. So you require these 3 variables, but it is not convenient to represent all these 3 variables on a board or a paper, because this leads to 3-dimensional figures. 3-dimensional figures. 3-dimensional figures. And this 3-dimensional figure cannot be conveniently written or represented on a paper or the board. Then what to do? For this purpose, out of these 3 variables, let us keep one as constant. One as constant. You can keep this as constant. When you keep temperature as constant, then you write the diagram between pressure and composition. That becomes PC diagrams. PC diagrams if T is constant. Similarly, if P is kept constant, then that becomes TC diagram. So TC diagram if P is constant, PC diagram if T is constant. Okay? So now it becomes a two variable diagrams which can be easily written as shown here. This is the one of the examples of lead silver system. For lead silver system, here the diagram is between temperature and composition. In this case, P is kept constant, and this is the TC diagram where P is kept constant. Okay, since out of these 3 variables, one is reduced, and therefore this phase mode equation changes to F is equal to C minus P plus 1. From this I have reduced one variable is reduced. Therefore, this is the new phase mode equation, F is equal to C minus P plus 1, which is called a reduced phase mode equation. Reduced phase mode equation or condensed phase mode equation. Reduced phase mode equation or condensed phase mode equation. And this expression for this is F is equal to C minus P plus 1. Here I have reduced one of the variables. Okay, pressure is kept constant for the solid two component systems. For the solid two component systems, usually the pressure is kept constant, and we will discuss only the EC diagrams for the solid systems, solid two component systems. And whenever we describe this one, let us use only the reduced phase loop equation. So what is the definition of reduced phase loop equation? Okay, the definition is, in this reduced phase loop or condensed phase loop equation, out of the three variables, the pressure variable is kept constant for the solid two component systems, and that is called the reduced or condensed phase loop equation. Now we should take up the examples of two component systems. If you take the examples of two component systems, we have three cases. First case, two component systems with detecting points. Detecting points. Number two, two component systems with congruent melting point. And number three, two component systems with non-congruent melting points. So we shall discuss these three: two component systems with eclectic points, two component systems with congruent melting points, two component systems with non-congruent melting. Okay, and in this case, in the first case, we have two examples. One is a lead silver system, and one is Ki water system. Ki water system. Let us discuss those two in today's class. Two component systems, and I shall discuss lead silver, potassium iodide water system, and for this one, two component systems with congruent melting point, we have Fe2Cl2 water system, hydrated ferric chloride system. Okay, this is the example for the two component systems with congruent melting points, and for this one, the example is sodium potassium system. Sodium potassium system. So we have discussed these one by one. Today, I shall go for the first one, in the two component systems with detecting points. In this one, I shall take up first lead silver system. The diagram is written there. The diagram is written there. Let us A, O, and B. See here, the point A represents the pure melting point of lead. The pure melting point of lead. Point B represents the pure melting point of silver. Okay. A is the melting point of pure lead. B is the melting point of pure silver. Now, when you add silver to this one, when you add silver to this lead, the solubility of silver in lead happens here, and the curve decreases like this, and it reaches up to the point O. So there is a decrease, there is is a decrease in temperature. There is a decrease in temperature of lead when silver is added to lead. Okay, so therefore the temperature decreases and finally it reaches point O. So on this line, you take any point on the line AO. You take line AO and you take any point on the line AO. It consists of two phases. It consists of two phases. What are those two phases? Means solid lead plus the solution of lead and silver. Along the line AO, you take any point here that consists of two phases. One is the solid lead and one is the solution of silver in lead. Okay. Now, if you reach point O, at this point O, there are three phases. What are those three phases? Means solid lead plus solution of this solution of silver plus lead, as well as solid silver. So these are the three phases which will exist at this point O. Further addition of silver to lead does not decrease the temperature. Okay, and therefore this is the minimum temperature attained in the diagram, and this temperature is called eutectic temperature. So what is eutectic temperature? It is the minimum temperature obtained in lead silver system when silver is added to lead. Okay, and this minimum temperature is known as eutectic temperature, and this composition is called eutectic composition. So this is briefly about this line AO and the point A and O. So at point A, there is only one phase, namely pure lead. Along the curve AO, there are two phases, pure lead plus the solution of lead and silver. Okay, and at point O, we have three phases: solid lead, solid silver, and the solution of silver and lead. Coming to this point also, same thing. At point B, it is the melting point of pure solid silver, I told you. So here only one phase. At this point, there is only one phase. Now it decreases in B, O, and you take any points on this curve. You take any points. At that point, we have two phases. One is the solid silver plus the solution of silver and lead. Here it is again decreasing. Why it decreases? Means when you add lead to silver, then the temperature falls. So you take any point on the curve BO, what happens to the melting point of silver? The melting point of silver decreases once if you add lead to the silver. So if you take, suppose if you take this point, at this point we have two phases. One is solid silver plus liquid. Liquid means the solution of silver and lead. That's called liquid here. Okay? And again, this decreases takes place up to the point O only, and further decrease is not possible even if you add a lead. Okay? So that point is called the eutectic point, and I told you already, what do you mean by electric point? The electric point represents is the minimum temperature and minimum composition of iron. Even the further addition of lead to the silver or silver to the lead does not decrease the temperature further, and that minimum temperature is called the eutectic temperature, and this minimum composition is called eutectic composition. So this is a brief look about the lead silver system. So finally, let me make that here one phase, here one phase, and you take any point on this curve or on this curve that consists of two phases. In this case, liquid plus solid lead. In this case, liquid plus silver solid. Here liquid means the solution of silver and lead. Here also the liquid means the solution of silver and lead. And at this point, I told you already, there will be three phases. One is solid lead, one is solid silver plus solution of silver in lead. Okay, so this is the minimum temperature and minimum composition. This is called eutectic temperature. This is called eutectic composition. Now we shall apply this to desilverization of lead, and the process is known as Parkinson's process. So how do you get this one? That I shall explain now in brief. So to explain desilverization of lead, and the method is known as Parkinson's process, let us apply phase rule for this purpose. Let us take urgently ferrous. Urgently ferrous lead. I have taken urgently ferrous lead. For this one, I am applying the phase rule equations, the phase rule principles. I am applying the phase rule principles to get more and more amount of silver, from this urgently ferrous lead. The concentration of silver from urgently ferrous lead by using phase rule principles is known as desilverization of lead. Okay, and the method is based on phase rule principles, and this is done by Parkinson's, and hence the name Parkinson's process. So that is about the desilverization of lead. Okay, let me repeat. The concentration of silver from urgently ferrous leads by using the phase rule principles is known as desilverization of lead, and this method is called Parkinson's process. I should tell you, the urgently ferrous lead contains less than 0.1% silver. The urgently ferrous lead contains less than 0.1% silver. Okay, now let us take lead. So to this urgently ferrous lead, if I add silver, so it will combine with the lead. It will combine with the lead and forms the liquid solution. Okay. At the same time, the amount of silver in adjuntiferous liquid goes on increasing from 0.1%. It will decrease like this. When it decreases like this, okay, why it decreases I told you already. Once if add silver to this lead, its melting point decreases along the current AO. So once if it starts to decrease, the amount of silver starts to separate. The amount of silver starts to separate out from this adjuntiferous plate. Okay, so this process increases the percentage of silver up to this stage, and I told you at this stage the amount of silver has increased to 2.6% from 0.1%. So that means the composition of silver is increased. The composition of silver is increased from almost less than 0.1% to 2.6% by adding silver to adjuntiferous plate. So this increase in composition of silver from adjuntiferous plate by adding silver is based on the phase rule principle, and this method is called the desilverization of lead. That means I am separating more and more silver from the lead. Okay, and this is called the desilverization of lead. This is based on the principal phase diagrams, and this method is called Patterson's process. So this is a brief look of the lead silver system. Okay. Similarly, if you take the next system, potassium iodide water system, the diagram is almost like this. So this temperature composition, okay. So this is potassium water system, and you just remember the difference between the earlier diagram and this diagram is this curve never cuts this axis in a cut, because the melting point of potassium iodide is very high, which cannot be represented on the diagram. So this does not cut this temperature axis. Okay, and here it is the ice, here it is the potassium iodide, and this is the, you take the composition, you take the temperature. Same explanation. Here it is the melting point of ice, A, O, B. Melting point of ice. This is the melting point of potassium iodide. Okay. To this ice, here it is only one phase, that is ice phase. Here also there is only one phase, namely solid potassium iodide. Now, to this ice, if I add potassium iodide, the temperature starts to decrease. Okay, and to take any point on this line AO, so that point consists of ice plus solution of potassium iodide. ಇದಕ್ಕೆ ನಾನು potassium iodide ಹಾಕಿದಾಗ potassium iodide will be soluble in water solution of potassium. So here there is only one phase, namely ice phase, and here you take any point on the curve AO, there will be two phases. One is the solid ice, okay, solid water means it's the solution of potassium iodide. Once you reach the point, you go here, again you get three phases. Three phases means ice, then solution, then solid potassium iodide. Solid potassium iodide. So this is the three phases. And you can apply phase rule equations. For this one, if you apply phase rule, here you have to use condensed phase rule, T minus T plus 1. The two component system. Here the number of phases is 1 plus 1. So that means it's 2. F equal to 2. That means to describe this one, to describe this point A, you require two variables. You require both temperature as well as composition. Coming to any point on this curve, there are two phases. I told you there are two phases. Ice plus solution of potassium iodide. Then if you apply this equation, F is equal to 2 component, 2 phases plus 1. That means 1. That means to describe any point on this curve AO, you require any one variable. You require either composition or temperature. If you know the temperature, automatically the composition will be fixed, or if you know the composition, automatically temperature will be fixed. So you require only one variable. And coming to this point, this point I told you is called eutectic point, and below this point, the temperature does not come down and even the composition does not change. Such a mixture is called eutectic mixtures. And here there are three phases. Ice, the solution of potassium iodide, and solid potassium iodide. Okay? Solution is here is potassium iodide plus water. So three phases are there, and you apply this phase rule equation. That is equal to 2 component, 3 phases. So to describe this point, you don't require either temperature or composition. In all these cases, the third variable, namely P, is kept constant. Okay, that is the standard thing you have to remember. And these diagrams are called TC diagrams. Therefore, I am applying only the condensed phase equations. Similarly, you can also explain this curve. This is the pure melting point of potassium iodide. It's only one phase. Then now we are adding ice here. If you add ice to this potassium iodide, the temperature will start to decrease. And you select any point on this curve. Any point on this curve consists of just namely the solution of potassium iodide and water plus solid potassium iodide. So these are the two phases written on this curve. And again, if you come to this point, again think this. Solid potassium iodide, the solution of potassium iodide in water plus you can say ice. That is the solid water. So these are the three phases. So this is brief about the potassium iodide water system, and these two systems, the lead silver system and potassium iodide water system, they come under the two complex systems with eutectic points. In the next class, I will discuss the other two systems with congruent melting points and non-congruent melting points. If I discuss those two complex systems, then this chapter will be over. So in the next class, I will do it. Thank you. Bye.